And 5.5 is all about the law of sines. And as I mentioned in the video, you're going to be given the formulas. We're going to give those on a piece of paper to you along with the test. But what you have to remember is when you can use which formula, because we don't just have the law of sines, we have the law of cosines as well, and we have a lot of other formulas. So the key to knowing this, because it's not a hard formula to use, is that it works for angle, angle, side, and angle, side, angle. And that, if it feels a lot like geometry when you were talking about triangle congruence, it should. We're kind of checking for those pieces that you had to check for congruence. And then side, side, angle, which many books, many geometry books have just thrown out, including yours. So when you were in geometry, there wasn't a side, side, angle. In older geometry books, I mentioned, they talk about that situation. Side, side, angle does work for triangle congruence if it's the biggest side opposite the biggest angle, and then the other side is just one of the other two that you have. But this is a case that's going to take us a little bit more work to see whether or not we actually can get a triangle and then use that law of sines for that triangle. So it feels wrong, but this is where I stopped. So basically, the video was the first page. That's what it was, because I didn't want to get into the heart of side-side angle, because that's the piece that makes this a little more complicated. And it's called the ambiguous case. Ambiguous means, well, we're not really sure whether or not it's going to work or not. And so that's what we're looking at here. Sometimes side-side angle will work, and we'll get a triangle. In fact, sometimes we'll get two triangles from the side-side angle case. But there are times when you cannot form a triangle with side-side angle. So in the side-side angle case, two sides and a non-included angle, the ambiguous case does exist. This information does not necessarily make a unique triangle. It might not form one, and possibly no triangle at all. In fact, depending on the proportion of the side lengths to the angle, it could form 0, 1, or 2 triangles. And here's the visual of why. So let's say we're given angle A, side length B, and side length A. And like it says, notice that we have a repeated letter in this case, which is the angle and the side that's opposite that. Now what we're going to do to make sure that we can always check these is we're going to set these all up the exact same way every single time. Whatever angle they give us, we're going to put it right here. And we're going to put the side opposite that angle over here because that's where it needs to go. And then whatever letter they give us for the other side, that's going to go adjacent to our angle. So that if you read this off, again, it feels backwards because it's counterclockwise. Side, side, angle is what we have. Now we need to set those up that way every single time, because then there's an easy way to tell whether or not you're going to get no triangles, one triangle, or two triangle. So here's how it works. They give us these side lengths, we put them on here, and we see the side length for A. Now if the side length for A isn't even long enough to reach the bottom of our triangle, that would be the height of the triangle or the altitude of the triangle, well then we can't form one. I mean, if this is the length that I'm supposed to use, and all I can do is just swing it back and forth. Oh, it's taking the blue one now. Let me get this one. It's never going to reach the base. So it's never going to form a triangle. It's just going to be a bunch of segments and an angle hanging out there in space. There's no way to get a two-dimensional object out of it. However, if, when we set this up as side, side, angle, we find out that A is just long enough. In fact, it's exactly equal to the height or the altitude. Then that forms one triangle. It's possible that it's longer than that. So we take a look at A, we figure out its height, and what we always have to do is compare it to the height of the triangle itself. If A is longer than the height, Well, then of course it's going to reach. But there's a possibility that the side could be over here, or it could swing over and hit it again over here. And that means it could form two triangles, and we have to evaluate both of those. So this situation, depending on how angry my smartboard gets with all this morning, would be, let me turn it around, like so, would be where we can take this side and kind of swing it like a pendulum. That's not going to let me do it perfectly, but I can show you moving it over. So we could get the one big triangle on the outside, or we could get this little sliver of a triangle that we see that's formed. So that's why there are two triangles that are possible there. And then the last one, this one has the side long enough so that if we did swing it like a pendulum, there's no way it would hit that triangle again. It's too long. It's going to go over to the other side. So all of these situations have to do with us knowing the height of the triangle. And once we know the height, we can figure out, will it reach all the way down? Is it at least as long as the height? Now, is it long enough that it would hit once and short enough that it would hit twice and get us two triangles? Or is it so long that we're not going to get anything but one triangle? Ben? Oh, we just get the one isosceles triangle then. Yeah, that's a really special situation where you get an isosceles triangle in that one. So this is all about the height and comparing that A value. So it's helpful to identify the ambiguous case from the beginning of the problem, then draw the information the same way every time. We want to set those up so that we have the angle, the side opposite, and the side that's adjacent to it, first side angle. And if you do that every single time, then the analysis gets much easier when you go through this. We're now going to analyze two different cases based on a given angle. The one that takes the most time to figure out are acute angles, because they'll form an acute triangle, which may give us the 0, the 1, or the 2. Obtuse triangles, not quite as bad, not as much to check. So in the acute case, B is less than A. So in this case, I see definitely B is less than A. And what I would have to do is figure out what is the height of that triangle. Will that side length of B even get me to the base? And it's some pretty easy trig to figure out what that height is, because we're just going to make it a little h, and we'll say, well, here's B. Let's see, I need h. I might as well just use A. I'm going to have that information. That's opposite and hypotenuse. That's sine. So if we do the sine of B equals h over A, we'd multiply both sides by A and get A sine of B equals h. So we can use sine every time to figure out what the height is. Now, if B is not as long as h, we're not going to get a triangle. And down here you can see all they did was substitute in B is less than A sine of B, because that's the math we would do to figure out h. We'd write 0 triangles and move on, because we can't solve that triangle because it's not a triangle. There aren't any. Now case 2 says we've got our triangle set up, side angle. Remember, it's counterclockwise there. And B ends up being perfectly the same as h, as the height. We're going to get one triangle, going to be a very nice one right triangle that we have, but we'll just write down one triangle. Now the third case over here, this is where things get a little weird. And that's because we're going to figure out what the height is, but what's going to happen is B prime is going to be greater than the height. So we know we're going to get 1 but it's possible we might get 2. So what we have to do is figure out, if we were to swing B prime on a pendulum back to the other side of the triangle, would it hit the base, the bottom of the triangle? And for that to happen, B prime has to be less than A. So B prime is going to be greater than the height, but it's going to be less than A. That way we'll know it's going to hit twice. Case 4. Ben asked about this one. What if B is exactly the same length as A? Special circumstance. One isosceles triangle. That's what's going to happen. So like it says right down here, one triangle, that's it. Because if we made this side a pendulum and we swung it over, it would hit exactly at angle B because it's isosceles. And then case 5. Here's our B. It's long enough that if we swing it over, it's not going to hit the base of that triangle again. So there's only one triangle that can be formed. So this happens when B is greater than A. It's all about comparing it to the height of the triangle and then visually thinking about, okay, if it were to swing around like a pendulum, is this going to hit again? How many triangles will I get? Like I said, it's much easier for the obtuse triangles. If we set up an obtuse triangle, it's going to be incredibly obvious that B is going to be too short if B is not greater than A. We're not going to be able to get a triangle out of that. In fact, if B is equal to A, we're not going to get a triangle out of that either, because they're matching up exactly at B. You'd never reach that base down there that you'd need for 3 sides. So for obtuse triangles, all we need to check is B greater than A? If it is, we can form a triangle. So this one usually doesn't take too much to think your way through. Now, don't memorize this little box. Like I said, think about the swinging pendulum and things will go well, but this just tries to summarize all the possible things that could happen when you're trying to figure out, do I have 0, do I have 1, do I have 2? So if you get confused when you're doing the homework, yeah, come back to this, reference it if it makes sense to you, but it's not a memorized thing. It's about drawing them and getting a feel for how many triangles am I going to have. So here we go. We're not trying to solve them. We're just trying to figure out how many are we going to have. Determine the number of triangles ABC formed by the given information. We always set them up the same way. So here's B at 122 degrees. We don't have to make our sketches to match any of that. But B is 122 degrees. Now we're always going to put that in the bottom left-hand corner. And the next thing we're going to look for is, what did they give me for a side length opposite that? So my side length opposite is always little b, and that's a 3. I don't know if that's going to reach or not. Got to think about that for a minute. And then our A value, we're always going to put that as the adjacent side to our angle. So there's our lowercase a, which means our uppercase A would be down here. And that would be our B. Now, is this an acute or an obtuse triangle? Obtuse. Got this 122-degree angle, right? The only way we can get ourselves an obtuse triangle out of this is if B is greater than A. Is it? No triangles. Not going to happen. So being obtuse means the only thing we have to check is the side opposite greater than the side adjacent? That doesn't happen in that one. B, they change up the letters, but we don't care. We can put C down here. C is 56. 56 degrees. I need to set up that side opposite. That's going to be little c over here. as 11.5. And then I need to use the other one as my side adjacent. So that's going to be 11. And that's going to make this capital A and this capital B. Now, this is acute. Going to take a little more work. So what I have to do is figure out what is the height or the altitude of this triangle so that I can compare this to see, am I going to get one triangle, am I going to get two triangles, what's going to happen here. So the sine of 56 degrees equals h over 11, opposite over hypotenuse. And we're just talking about this small triangle that we cut off when we put the height in there. And then 11 sine of 56 degrees equals h. So now's a great time to grab your calculator because we're going to need those quite a bit today. And we will be using degrees, so we have to make sure the mode is changed into degrees. And we need 11 sine of 56. So 9.119. So now we can get one triangle if C is longer than 9.119. Yep, we've got one triangle, but there's a possibility there might be two. So now, if I swing 11.5 over to the other side of the triangle, is it going to hit the base again? Nope, because this is only 11. So the 11.5 will be too long and it'll hit out here somewhere. It's not going to hit the base. One triangle is all we get for this one. Alrighty, let's go to C. So with C, we have A as 36 degrees. Again, always setting that up as our lower left-hand vertex. That's 36. Go to the side opposite. A is 7. And then lowercase b will be adjacent, which makes the lower right-hand vertex capital B. And it leaves C for the top. 7 sounds kind of short, given that we have a 12 on the other side, but it's also 36 degrees. So we better check the height. And again, I've split this into two triangles. Now we just want to use the leftmost triangle to check on that height. So the sine of 36 degrees equals h over 12. 12 times the sine of 36 degrees equals h. Let's punch it in and see. .053. Is A long enough to get to 7.053? A was only 7. It's going to be a teeny bit short. It's not going to make it down to that base. We're not going to get a triangle out of this one. We don't get one. Has to be long enough to reach the base of the triangle to form a triangle. D. By now, hopefully you're putting that lower left corner always as that angle without me telling you about it. And then we've got our lowercase b for the opposite side. The other side always goes to the adjacent side to angle B, or whatever angle they give us. So there's our A, which means our capital A would be down here. And this would be a C. So it's acute. Got to check. Let's drop down that altitude, that height, and find it. So the sine of 45 degrees equals h over 7. Now we know the sine of 45 degrees, hopefully by heart, but we're going to want to see it as a decimal anyway because we want to know whether or not that 6 is going to reach it. So usually we'll just punch it in. 4.950 with rounding. Six is the side that's going to have to swing. Is 6 longer than 4.950? It's going to reach it. So the 6 is bigger than this height. It's going to reach it. Might reach it again. This side is longer than the height, so we get at least 1. We're going to get 2 if, when we swing this 6 over here, it lands and produces another sliver. Will it? Yep, because this is a 7. So it's going to hit. It's shorter than 7, and it's going to hit again. This one would give us 2 triangles. So our value for the opposite side was greater than the height. We know that gives us at least 1. But if it's also less than the side that's adjacent to our angle, then we can get 2 little triangles formed. Alrighty, E, 170 degrees, wow. So there's our C. Side opposite. Side adjacent. Put my little 170 degrees in there. We're going to get a triangle for this one. Remember, for obtuse, all that has to happen is side opposite has to be greater than side adjacent. Yeah, we're going to get 1 triangle out of this. Again, it's the acute that takes a little bit more math, where we have to check out the height. All right, F. There's our capital A, our vertex at 55 degrees, little a, 3.8, and then they have C. So opposite that's going to be our capital C, and that would make this one B. Well, we better check out the height. The sine of 55 degrees equals 3.8. Oops. Equals h over 4.6. Looking at the wrong triangle over there. So 4.6 sine of 55 degrees is h. And we'll pop it in and see what we get. .768. Is 3.8 longer than 3.768? So 1 at least is 3.8 less than 4.6. We're getting 2. Oh, I probably better keep this consistent and just put 2 triangles with the numeral 2. So this is the first thing we need to do whenever they say solve a triangle, and all they do, they don't draw it for us, is they give us a side-side angle situation. Once we've done that, well, then we have to solve it. We have to know, are we looking for 1 triangle, or are we looking for 2 triangles? You know, how many triangles are we talking about here before we get started on trying to find them? So here's example 2. And example 2 gives us a little too much information. Notice it says side-side angle right up there. So solving a triangle given 2 sides and an angle. That's the first thing we'd want to check. You know, what type of situation are we talking about here? Because if this is angle, side, angle, and angle, angle, side, I can just use the law of sines right away. I don't need to do any of this checking business. But we look at the information and we see 2 sides and an angle. This one is drawn for us. So same drawing we've been doing. Here's our lower left-hand corner for the vertex, side opposite, and side adjacent to it. So since it says solve triangle ABC, I need to know, well, is there going to be 0, 1, 2? I mean, that is not drawn to scale. I'm sure of that. They never draw them to scale. So the first thing to do would be, let's figure out the height. See what that is. Sine of 26.3 degrees equals h over 6. 6 sine of 26.3 degrees equals h. .658. All right, so is 7 longer than 2.658? So we've got ourselves a triangle, one triangle here. Now, is 7 less than 6? So we do only get 1 out of this one. So if this is our one triangle, it shouldn't take us too long to find all the other parts. And now we know we can go ahead and use the law of sines because sine side angle did work. It's not ambiguous anymore. We know we're going to get a triangle. Now that means what I have to do is find that angle that had an opposite side paired with it so that I can use that in my proportion. I need numbers, numerical values for those. And that's always our big angle that we have in the lower left and the side opposite. So sine of 26.3 degrees over 7 equals. And then it's up to us, what we want to find next, but the only other number they have for us up there is a 6. So if I'm going to use the 6 to find something, I have to use the angle that's opposite the 6. So that's going to be the sine of angle B. And now I have to cross multiply and figure out how I can get angle B out of this. So it will be 7 sine of angle B equals 6 sine of 26.3 degrees. And then I'll have to divide both sides by 7. But then I have to remember, how do you get the angle back? Because that's what I'm looking for here. Right now I have the sine of B. And to get the angle back, I'm going to have to use the inverse function. So I'll need the inverse sine of 6 sine of 26.3 degrees over 7. Doesn't look like a decimal there. And that will give me the measure of angle B. So once again, we're writing all the math down perfectly until we don't have any choice, and then we have to punch it into the calculator. So I'm going to do 6 sine of 26.3 degrees, which we had in there just a minute ago anyway, and divide that by 7. And then I want the inverse sine of that answer because I want to know what angle that represents. So second sine, second negative, that calls up the last answer I had, keeps it in there perfectly, and enter. So it is 22.320 degrees. Now, I should think ahead whether or not I'm going to need that 22.320 that I have there. And here's why. Because remember, we don't want rounding errors. So if when I'm doing my next planning I realize I'm going to need to use that, we're actually going to start storing things in our calculator. Maybe you just store it because you're not sure whether you're going to need it anyway. Now this was the measure of angle B. So let's just say we want to store this just in case. We're going to hit the store button, which is STO. It's just to the left of the 1. And then we're going to tell it where to store it. And since this was angle B, I'm just going to name it capital B. So I have to hit alpha, and then I have to look for the little green B. And the little green B is on the apps button. And now when we press enter, it's going to store all of those decimals, all of that information for us into B. And it's usually a good idea, especially when you have 2 triangles that you have to work with, to leave yourself a little note. And what I do is I kind of make a little calculator button looking out of it, a little rectangle thing with a B there, so I'll know, hey, if I need this, this is stored. I can use my decimals as perfect answers in there. All right, so what else do we need? Well, we know the measure of angle A, they gave us that. We know the measure of angle B, they gave us that. We're going to need to know what the measure of angle C is. So, the measure of angle C, every triangle is 180 degrees. We're going to have to subtract the 26.3 degrees, and we're going to have to subtract the number we just found, 22.320. But I started thinking to myself, oh, I rounded that. I'm going to get a rounding error. Not if I stored it, and I used the stored value to figure this out. So we need 180 minus 26.3 minus that stored angle that we have in here. So we'll do minus alpha B. And the calculator takes that nasty decimal that we had and puts it right in there for us. Enter. 131.380. degrees. Now I'm planning ahead again, and I realize, well, if I'm going to figure out what little c is, I'm going to have the sine of angle C. So I better store that C in there so I can use that. Store, so store alpha, and C is the program button. Now it's in there if I need it. I put my little calculator button icon there so I can remember that I have it and where it is. And now all I need is little c. Well, I have to have a proportion again, and I'd rather stick with things the book gave me if possible. So I'm going to stick with this sine of 26.3 that they started me off with over 7. But here's where we realize, yeah, we're going to have to use that c value that we found. So the sine of c over, and in this case that'll be our little c. Now, we have taught you that elegance means we can't write down our little rounded answers. But with a problem like this, we don't have any choice. You know, we have to write down that we found 131.380 right here. But what we're not going to do is use that rounded value. We're going to use the value that we have stored in our graphing calculator. So C sine of 26.3 degrees equals 7 sine 131.380 degrees. Divide both sides by the sine of 26.3 degrees. And that will get us C. So we're going to need 7 sine of what we stored as C and then I have to divide that by the sine of 26.3. $11.854. And now I'm looking around for labels. But what usually happens in these problems, unless they're a word problem, is they don't give us any labels. So as I mentioned on the video, you can put a little U for units if you want, but we don't take off points if you don't label them, if they don't give you a specific unit. Now, when I'm done with these, that's a lot of work. Can you imagine how many points something like that would be on a test? I'm going to make sure I have absolutely everything. So I'm going to make a little inventory list of, do I know the measure of angle A? Do I know the measure of angle B? The measure of angle C? Do I know what little a is, what little b is, and what little c is? Just so I didn't forget anything. So that's a lot to keep track of. Well, the measure of angle A, they gave us that one. That was 26.3 degrees. The measure of angle B, we found that one. We did have to round 22.320 degrees. C, we found that one. Again, we did have to round 131.380 degrees. Little a was given to us as 7. Little b was given to us as 6. And then the last piece of work we just did was figure out little c. Now imagine doing that twice for one problem. Because when we have situations where we have two triangles, we have to go through this process for both of those triangles. And that's what we're going to have to do in the next one. Ben? The Pythagorean theorem? We don't have right triangles. Let me take a peek at what you're talking about. Oh, okay. So you're saying in those two triangles that we broke apart there. No, no, because, well, first of all, because this is about the law of sines, so we're supposed to get the work in there for the law of sines. But there's going to be, you'd have to add two different pieces together, and rounding errors would get additional rounding errors. Might be a good way to check, though, Ben. I mean, if you have time when you're done with the test, go back and check and make sure that your values do work when you put them in the Pythagorean theorem. Now, you may have noticed with this last one, we wouldn't have had to store C since it was the last thing that we were working on. We could have just pulled it up as the answer. But better to be safe than sorry, because there's nothing that makes you more furious than getting 3/4 of the way through a problem and realizing, oh my gosh, I forgot to store an angle that I needed earlier, because then you have to go back and punch it all in again. So overstore, don't understore. Now, I was hoping we could get through this one. Maybe we can get through at least part of it. So this one is handling the ambiguous case again of side-side angle. That's where we spend most of our time because that's where most of the math comes from. Solve triangle ABC given that A is 6, little a is 6, little b is 7, and the measure of angle A is 30 degrees, which is actually a special one since we know about 30, 60, 90s. But the first thing we would do, and I know they already did it for us, but we would figure out that height to see that we have two triangles. So the sine of 30 degrees equals h over 7. 7 sine of 30 degrees equals h. And this one goes much faster if we remember the sine of 30 degrees is 1/2. Otherwise you punch it in. You get the same answer. So yes, 6 is greater than 3.5. And it's less than 7. So it is going to form the two triangles. It forms one large one, and then it forms a little sliver triangle right here. So let's get busy. We've got a lot to figure out here. Well, as I think about using the law of sines, since side-side angle gives me that information that I should use the law of sines, I realize I have the 30 degrees and the 6 to use in my proportion. And I realize, again, they gave me the side opposite B. So I'm going to have something with that 7 if I'm going to be able to solve this. So this feels a lot like the problem we just did because they've got, dropping things, they have the triangle set up very similar. Now we need the measure of angle B. So we cross multiply. And we divide both sides by 6. And we realize we're going to have to take the inverse function if we want to know what that angle is. So we need the inverse sine of 7 sine 30 degrees divided by 6 to get the measure of angle B. 7 sine 30, which we should not be shocked is 3.5, divided by 6, and then inverse sine. So second sine second. Answer 35.685 degrees. Double check that one. Okay, every once in a while I transpose numbers, so I want to check that I wrote 35.685, which is what we saw on the screen. I'm going to need that. I know that. I just did a problem just like this. I better store that. So store, and it's B, so why not put it in B? I can just override what's already there. Alpha B. Now the new one is in B. Put my little calculator looking button there so I remember that that's there. Well, now we've got A and B. We can find angle C. Let's find it. 180 degrees minus 30 degrees minus our 35.685 degrees. So 180 minus 30, which is of course 150, minus alpha B. So 114.315. I'm going to store it. Better to be safe than sorry. Store alpha C. So I've got it in there and ready to go. Because I have one more side length that I have to find. I'll go back to the sine of 30 degrees over 6. I'll need the sine of my angle C, which again, I know this breaks our rules of not writing down decimals, but we don't have any choice when there's this much math involved in a problem, this much algebra that we have to do. And then cross multiply. And divide by the sine of 30 degrees. So again, we write down the answer as close to perfect as we can before we punch it in. So that was what was in my angle C. So I need 6 sine of C. And then I have to divide that by the sine of 30 degrees. .936 with rounding. Go back, check and see, did they happen to give us units this time? No, no such luck. All right, let's take an inventory here. A, they gave us angle A, the measure was 30 degrees. Measure of angle B, first thing we found, 35.685. Measure of angle C, we just found that, 114.315. Little a was given to us, that was 6. Little b was 7, and we just found side length of C at 10.936. Now we have to do it again, because there are 2 triangles that might be formed here. So I start thinking, something in all that math I did must help me out with this one. And there is one thing that helps me out, and that's the fact that I found angle B. Right there. Because this triangle that's formed, that's in the dashed lines right here, that's now an isosceles triangle. Remember, we had to take this side and we had to swing it over to the other side of the base. So that means if this little angle is 35.685, so is that one. And that's going to help me figure out what the measure of angle B is. Now, I'm not going to call it B anymore because that'll confuse it with what we did over there. I'm going to do B sub 2. So the first thing I'm going to figure out is what's the measure of angle B sub 2. Well, those 2 angles, B sub 2 and B, form a straight line. And straight lines are 180 degrees. And again, I'm really glad I stored something. You know, I've got that 35.685 right in there as B. So I can take 180 minus B. 144.315. Chances are pretty good that I'm going to need that again. Now, if I'm worried that I'll override B and I just used it for something, then store it as D. You know, store it as something that's totally different. It's totally up to you what you store this as. So again, if you're worried at some point you're going to need to go back and use that B angle again, store it under a different letter. So there it is. So now in our little sliver of a triangle, we have the 30, we have the 6, we have the 7, and we have the measure of angle B sub 2 as 144.315, which means I can now figure out the measure of angle C sub 2. Because in that little sliver of a triangle, there's still 180 degrees. And I still know that angle A is 30 degrees. And I know B sub 2, 144.315 degrees. And I stored that as D. So 180 minus 30 would be 150. And then I want to call up my angle D. 5.685 would be the other angle. Again, I'm doing that sub 2 since this is my second triangle. And now I need the new length for little c. So sine 30 degrees over 6, still sticking with the one they gave me, equals the sine of 5.685 degrees over c. Shoot, we'll have to finish that one tomorrow. You will be able to do the rest of the homework for day 1. Thanks for hanging in there. In fact, if you were punching in fast, you probably already have that little C, but I'll save it here so we can just finish that up tomorrow. Obviously, they take a while. There's a lot going on there.